A system is a small segment of the universe that we will consider in solving a specific problem. We will erect a boundary around that system. Any force or object outside of that boundary will not be considered. The environment is everything outside of the system boundary that we create. The system can be a particle, it can be a group of particles, an object, or an area of space. Its size and shape we determine by determining how we want to solve the problem. Why are we defining a system and its environment? We do that so we can make a problem solvable. By defining an appropriate system, we can isolate the forces that are within the system from the forces that act on the system from the environment. If the forces are internal to the system, then there's no change in the energy of the system. In this case, there might be if we have thermal energy, but we're going to talk about that in another unit. If the forces are external, then there will be a change in the energy of the system. But what is energy? It turns out that energy is so fundamental, like space and time, that there's no good answer to this question. However, just like space and time, that doesn't stop us from doing very useful calculations with energy. Here are a few things that we want to talk about. It has the ability to do work. It can be stored. It can be changed from one form to another, like from light to thermal energy, or gravitational potential energy to kinetic energy. Did you notice a term in the bullet list above that hasn't been defined yet? We'll talk about that in a minute. Which of the following are characteristics of energy? There's two correct answers. Pause now. Okay, let's see if you were correct. The correct answer is B and C. Energy can be changed from one form to another, and it has the ability to do work. A system is defined as, pause the video now. Did you choose D? Because that is the correct answer. A small segment of the universe that is chosen to facilitate the solution to a problem. Forces internal to the system cannot change its total energy. Let's talk about work. In the previous slide on energy, it mentioned work. So what is work? It is not what we talk about in common language. It's unfortunate that sometimes physics uses words that are used every day in quite a different fashion. So, for example, if you're holding a heavy box, do you think you're doing work? You're not. That's the problem with using these words in everyday life. Work in physics terms is defined as the exertion of a force over a displacement. And to further complicate it, only the component of the force that's parallel or anti-parallel to that motion is actually counted. If you're holding a box, you're certainly exerting an upward force to keep the acceleration due to gravity of the box at zero, or not affecting it, the gravitational force from being zero. Sorry. Cut that piece. If you're just holding a box, you are certainly exerting an upward force on the box. This keeps the acceleration due to gravity from having the box move. But there's no displacement. That means there's no work done. The equation for work is equal to F dot D, or work is equal to the force times the parallel component of the displacement. So here you see the formal equation for work. Work is equal to F dot D. Force and displacement are vector quantities. If their unit vectors are in the same direction, for instance, I hat dotted with I hat, or J hat dotted with J hat, you get 1. If you have I hat dotted with negative I hat, or J hat dotted with negative J hat, you would end up with negative 1. When you have two unit vectors that are not the same dotted together, you always end up with 0. So if the force is acting in the same direction as the object's motion, that's I hat dotted with I hat, or J hat dotted with J hat, and that gives you positive work. If the forces act in opposite directions, then you're going to have a negative in there, and that means that work done is negative. If the object doesn't move at all, or there's no force applied to the object as it's moving, then the work is 0. The next slide will illustrate these 3 points. Okay, so in the first example, we have a force acting upward, but the displacement of the block is horizontal in the I-hat direction. Remember, j-hat dotted with I-hat is 0. Here, the force and displacement are in the same direction, and this gives us I-hat dotted with I-hat, which is 1, so the work here is positive. In the last example, notice that the force is being applied going west, or negative I-hat, and the displacement is east, or I-hat. Here, the work done is going to be negative. In which of the following cases is positive work done by the applied force? Pause the video now. Okay, let's take a look at our answers. A softball player catches a ball in her glove. That's actually an example of work being done. A force is being applied, and it is being applied to slow it down. So the displacement is going east, the force is going west, and that gives us a negative work. A homeowner is applying his force to move his lawnmower from rest. That is an example of work being done. A force is moving the lawnmower, and it has a displacement. A driver applies the brakes to slow down. There is a force being applied and a displacement. A student holds his textbook in front of him and does not move. No motion means no work done. If you have a very specific amount of using work, then we can look at the following thing. The system or environment that the work is acting on needs to be specific. So, for instance, an applied force does 12 joules of work on a box. Or gravity, or the force of gravity, does negative 5 joules of work on a box that is being raised up. This is not a complete statement. An external force does 6 joules of work. What's missing? The system or the environment that the work is acting on must be described. Net non-zero work can only be done to a system by an external force. In other words, a force that acts from outside the environment, or outside the system from the environment. So if our system is a box sitting on a table, and I come along and I push that box, I can increase the energy of the box. I am doing net non-zero work on the box. Why are none of the internal forces, like forces within the box, such as the box's molecules, moving about and colliding with each other, involved in the increasing of the energy of the system? The molecules are certainly exerting forces on each other, and they are causing each other to move. But remember Newton's third law. Every time a molecule in the box strikes another molecule, it exerts a force on it and moves it. However, the second molecule exerts an equal magnitude but oppositely directed force on the first one. Thus, assuming that we have equal masses for the molecules, the work done internally to the system actually equals 0. They all cancel out. Thermal energy also complicates this picture, but again, we're not going to talk about thermal energy in this unit. Let's do an example. A 36.0 Newton force is applied to an object that moves 11.0 meters in the same direction as the applied force on a frictionless surface. How much work is done on the box? Let's go ahead and check out the answer. We take work is equal to F dot D, and in this case, we're going to multiply the magnitude of the force times the parallel component of the displacement. Since the force and displacement are in the same direction, we multiply them together, and we end up with 396 joules. A 36 Newton force is applied to an object that moves 11 meters in the opposite direction of the applied force on a frictionless surface. How much work is done on this box? Let's take a look. Again, we look at the force and parallel component of the displacement. Here, the force is going west, and the displacement is going east. So we have negative I hat dotted with I hat, and that gives us negative 1. So negative 1 times 36 newtons times the 11 meters ends up giving us 396 joules, but notice here it's negative. A 36 Newton force is applied to an object that remains stationary. How much work is done on this object by that applied force? Did you already think that the answer should be 0? If you did, you'd be correct. The force is not causing a displacement. No displacement means 0 work done. A 2-kilogram block slides 4.5 meters to the right on a frictionless table with a constant velocity of 5 meters per second. What is the net work on the box? Since the box is moving with a constant velocity, there is 0 net force on the box. 0 net force means no work is done. The work should be 0 joules. Which law explains why internal forces to a system do not change its total mechanical energy? Pause now. Okay, let's check and see if you have the right answer. Did you choose C, the third law? If so, you are correct. A book is held at a height of 2 meters for 20 seconds. How much work is done on the book? Pause now. Let's check and see if you have the right answer. Did you choose E? If so, you're correct. The work done is 0. The book isn't moving. A book of mass m is lifted upwards at a constant velocity, a displacement h, by an external force. How much work does the external force do on the book? Pause the video now. Let's check your answer. Did you choose mgh? If so, you're correct. Or did you choose C, 0 work? Well, it turns out that even though this is lifted at a constant velocity, they're not asking for the net work done on the book. They're asking for how much work does the external force do on the book. Since there is an external force and a displacement of h, we take the weight of the book, which is equal to that external force, to give us a constant velocity, and that ends up giving us mg, and then we multiply that by the displacement, which is the height. That gives us mgh, or d. A book of mass m is lifted upwards at a constant velocity, a displacement h, by an external force. How much work does the gravitational force do on the book? Pause the video now. Okay, let's check the answer. Did you get E, negative mgh? If so, you are correct. Remember, the gravitational force is going down, but the displacement of the book is going up. That gives us negative j hat dotted with j hat, which is equal to 1. That means that the work done is negative mgh. A book of mass m is lifted upward at a constant velocity, a displacement h, by an external force. How much net work is done on the book by the external force and the gravitational force? Pause the video now. Did you choose C? If so, you are correct. There's 2 ways to get this answer. One, it's traveling at a constant velocity, which means the net force is 0, and 0 dotted with the displacement of h gives us 0. Or you could have said the work done by the external force plus the work done by the gravitational force added together would give us the total work exerted on the book. mgh minus mgh gives us 0. Now we're going to put it all together. Let's relate the 4 concepts of system, environment, work, and energy in terms of conservation principles. The most powerful concepts in physics are called conservation principles. These principles allow us to solve problems without worrying too much about the details of a process. We just have to take a snapshot of the system initially, and then after various forces have acted upon the system, and then we take another shot. By looking at these 2 snapshots and comparing them, we can learn a lot. So let's look at a conservation principle. A good example is a jar of candy. First, we define the system boundary, and the environment. The system includes the pieces of candy inside the jar. The jar is going to be the system boundary, and everything outside of the jar is the environment. If you know that there are 50 pieces of candy when you start, and no pieces have been added or taken out, in other words, no pieces have crossed the system boundary, then you know that you must have 50 pieces at the end. Now, you could change the way that you arrange these pieces, as shown in the pictures below, but you still have 50 pieces. In that case, we would say that the number of pieces of candy is conserved. That is, we should always get the same amount, regardless of how they are arranged, as long as we take into account whether they have crossed the boundary. Energy is a conserved property of nature. It's not created and it's not destroyed. So in a system where nothing crosses the boundary, we will always have the same amount of energy. This is called a closed system. The only way the energy of a system can change is if it is open to the environment. In other words, the system is no longer closed. If energy can be added or taken away, then we have an open system. Because of this conservation principle, we can do very useful calculations with energy. And unlike force, energy is a scalar quantity. It can be positive and it can be negative, but we don't have to worry about vectors. We're going to go ahead and start talking about conservation of energy in the next video.